All right, troops, here we go. I'm going to go through Chapter 2 review. Based on the pattern, what are the next two terms of the sequence? So remember, when you're looking at these, you want to look for any common patterns. So you just have to start analyzing it and taking a look. So we got 9 to 15, 15 to 21, 21 to 27. We can see that in each one of those we add 6. So what are the next two terms? Well, what's 27 plus 6? 33. And what is 33 plus 6? 39. So my answer would be D. Now this one's a little trickier. Based on the pattern, what are the next two terms? So when you're analyzing this, we're seeing the 9s. They all are the same. So I'm like, okay, the only way I would get them the same is if I was adding 0 on the top or multiplying by 1. So I'm going to see what happens in the bottom here. Oh, how am I getting this? I'm multiplying by 5 times 5 times 5. Okay, I think I got it. So we're going to multiply the top and bottom by 1/5 and get our new thing. Okay, so you can go ahead and grab your calculators and you can do 9 over 25 times 1/5, and that will be 9 over 3125. And then you're going to again repeat that and multiply it by 1/5. We still have 9 in the top, but the bottom is going to be 15,625, which would give us C. Taking a look at 3, what conjecture can you make about the 14th figure in the pattern? So if we look at that, I'm just going to not look at my answers right now because I just want to take a look at what we have. So if I'm talking about 14th, I can tell that we repeat the pattern right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Ding! I'm going to have a rectangle, so the answer is B. Next page. More conjectures. What conjecture can you make about the product of 13 and 8,888,888? Okay, so let's take a look. I'm going to see if I can get this just a hint crisper. When you take a look at that, first I'm looking at what they're doing over here. So I'm like, okay, all the 13s are the same. The only thing that's happening is they're adding another 8 every time. Okay, let's look over and see what's on the other side. Okay, so I can see that the 2 1s and the 2 4s always are buffering the inside. And the inside's filled with 5s. But how many 5s? When I had 2 8s, I had no 5s. When I had 3 8s, I had 1 5. 4 8s, 2 5s. So what ends up happening there is that the number of 8s minus the number of 5s that are in here are equal to however many 8s you have here minus 2, right? Because there was 2 8s minus 2, no 5s. 3 8s minus 2, 1 5. 4 8s minus 2, 2 5s. 5 8s minus 2, 3 5s. Okay, thought I was going to sneeze again. Excuse me. So let's look up here at this one. So the product of 13 and all these 8s. So 1, 2, 3, 4, 5, 6, 7 8s. And we're going to take away 2. So that leaves us with 5 5s. So we're looking for the one that buffers with a 4 and 1s on the ends and has 5 8s. Let's see here. 1, 2, 3, 4, 5, 6. Nope. That's got 3 1s. That's not even in there. That's got 3 1s. Nope. 1, 2, 3, 4, 5. There it is. See, these have 3 1s and 3 4s. Those are not an option. Okay, 5. What's a counterexample for the following conjecture? Come a little closer to this page. Hang on. There we go. I'm a little rusty on all this. Little rusty. What is a counterexample for the following conjecture? All quadrilaterals with 4 right angles are squares. Okay, so we're trying to think of a quadrilateral with 4 right angles. So finding the verb helps you. So there's my verb. So that cuts it. So I'm trying to think of a quadrilateral with 4 right angles that is not a square. That would be the conjecture. And the answer, of course, is rectangle. Because that has 4 right angles, but that is certainly not a square. 6. What are the hypotheses and conclusion of the following statement? Write it as in a conditional. So remember, a conditional is an if-then statement. So cats are animals. So again, if you're having trouble with these at all, find your verb. That helps break it into its 2 parts. So cats are in the if and mammals are in the then, but we got to make it make sense. So we would want to say something like, if the animal is a cat, then it is a mammal. So again, we're looking cat in the beginning, mammal in the then. Yep. But it also says to what are the hypothesis and conclusion. So I've done this part, but I have not done the beginning part. So we always want to make sure we answer the question fully. So the hypothesis is this part. The animal is a cat. And the conclusion is the then part without the then. It is a mammal. Next, what are the converse, inverse, and contrapositive? Which ones are true? So we're going to evaluate the truth value in this. I don't know why it looks so small to me. So remember, this is our if then, that's our P implies Q, right? This is my P, this is my Q. So in a converse, what it does is it flips it. Q implies P. And in inverse, it takes this and negates them both. So it's not P implies not Q. Contrapositive does both. It negates it and it flips it. So it's not Q implies not P. Now remember, the truth values are the same for these outer ones. So for the original, let me get a different color here. Original, these have the same truth value, meaning either if one's true, the other's true. If one's false, the other's false. And then these on the inside have the same truth value. If one's positive, the other's positive. If one negative, the other's negative. The other is negative. So let's write them. So remember, when we're doing our flipping, we're not taking the then and the if with it. We are simply going to, let's see here, I'm trying to figure out which color shall I pick. I'll do the red. The converse is the Q to P. So I'm going to take this and I'm going to flip the Q and the P, but I'm going to leave the if and the then. So if the square has area of 25 inches squared, I should have said has an area, 25 inches squared, then the square, I could have said it, has 5-inch sides. Okay, Is that true? If a square has an area of 25, then the square has sides of 5. That is a true fact. Yes, true. So I already know my inverse is going to be true. But let's take a look and make sure, because sometimes when you catch mistakes by checking them. So not P to not Q. So now I'm going to leave it like P to Q. It helps to label them, but I'm going to negate this and negate this. So if a square does not have 5-inch sides, then, I threw in the word not, then the square does not have an area of 25 inches squared. That also is true. All right, now let's do the not Q, not P. So I'm going to do if the square does not have an area of 25 inches squared, then it does not have 5-inch sides. Okay, so that one we got to evaluate the truth value, but remember it's the same as this truth value. So let's look up here. If a square has 5-inch sides, then the area is 25. Yeah, that's true. So therefore this is also true. Okay, so I would highly recommend on these, number 1, underlining and labeling them. And then 2, just writing them over here. The first one's the flip. The second one is the original negated. And the third one, the contrapositive, is the flip and the negation. It does both. The longest word does both. It flips them and it negates them. And that means that's the not. Okay, so let's look at 8. We didn't spend a ton of time, much at all actually, on Venn diagrams, but they're not too complicated. They're a visual to help you understand, you know, what's involved with what. So if I asked you to write a conditional about this statement there, I could either write it in an if-then or a straight statement. So I'm going to look at this, and I see that the circles, all of the squares, the whole circle, all of the squares are also what? Quadrilaterals. So I can say that all squares are quadrilaterals. That'd be one thing. Or you can also write it as if then. So if the figure is a square, then it is a quadrilateral. Now that wouldn't work the other way, would it? The other way, let's just pretend we had a circle and it was squares and we had a little one quads. Would that work? Are all quadrilaterals squares? No. Nope. That one would not be a true statement. That's how you would say it, but that's not true. All right, onward we go. So we're getting to some of my favorite problems, which, as you know, I say a lot. Is the following definition of dog reversible? If yes, write a true biconditional. Now let's remember that biconditional is an if and only if. It's not an if then. So it's a statement where this is in the middle. So you have something here, if and only if something. That's how a biconditional looks. It's also a definition is a biconditional because a definition has to work both directions. So that's why it's saying, is it reversible? In other words, is the if then true and is the converse true? Does it work both directions? Well, let's see. A dog is a mammal. So let's first get the verb out there. If it's a dog, then it's a mammal. Is that true or false? If it's a dog, then it's a mammal. That is true. And I'm frustrated. These keep popping up here. Then we have to decide if it's reversible, because that's true. If it's a mammal, then it's a dog. Not true. There's lots of mammals that are not dogs. So my answer for that one would be A. Next one. Is the following definition of perpendicular reversible? If yes, write a true biconditional. Two lines that intersect at right angles are perpendicular. Again, find the verb so you can see your if then clearly. So I have if two lines intersect at right angles, then they are perpendicular. Yep, that's true. If two lines intersect at right angles, then they are perpendicular. Okay, let's flip it now. If two lines are perpendicular, then they intersect at right angles. Yep, that would be true. Now, that means this is a great definition because it works both directions. So we can write a biconditional, which means I'm looking for something, first of all, in that form. If it's not even in that form, then it's not a biconditional. So we got an if-then statement here. We have another if-then. That's not what I'm looking for. It's not, it is reversible. Yes, two lines intersect at right angles, if and only if they are perpendicular. And that's it. Easy. 11, is this statement a good definition? So we're again going back to this idea that if it's a biconditional, it can go both directions, and that makes a good definition. If not, find a counterexample. A square is a figure with two parallel sides and four right angles. Find the verb. So we're talking about squares. So if we have a square, then we have a figure with two pairs of parallel sides and four right angles. Is that true? Yes, that is true. Let's try it the other direction, because it goes fine this way, but let's try the converse. If the figure has two pairs of parallel sides and four right angles, then it is a square. Two pair of parallel sides and four right angles, then it's always a square. No. Here's one where you have two pairs of parallel sides and four right angles, and that, as we all know, is a rectangle. And just so you know what a rhombus has something that has four equal sides. Parallelogram has two sets of parallel sides. So a rhombus, sometimes people think of like a kite, where all the angles aren't necessarily 90 degrees, but the sides are all the same. Or not a kite, like a diamond. A kite has different sides. Something like that, where these sides are all the same, but it's not necessarily 90 degrees. And of course, a parallelogram has parallel sides, but not necessarily 90 degrees. I mean, not necessarily. They have the two sets of parallel sides. So this is parallel, and this is parallel. All right, now we're getting to our justifications. So we have to name the property of equality or congruence. Remember the difference. Numbers are equal. Figures, shapes, are congruent. Okay, so we want to make sure we're keeping that in mind. That's how you know. I can see right away here that we're dealing with congruence, and I can see right away here we're dealing with equality. So make sure you add that to it. So if D is congruent to C and E is congruent to C, then D is congruent to E. This is, we have a connector there. It's the C's, and therefore D and E are the same, and that is the transitive property of congruence. So that will always, transitive will always involve three. It'll always involve two given statements and a conclusion. It's kind of like the why can I not say that? All of a sudden it's not in my head. Sniggleism. All right, maybe it's on the next page. I wonder if it is. Anyway, okay, so on to this one. We're looking at this statement and we're saying, how do we get to this statement? And any of you out there can solve that for sure. You divide by 4. And there you go. You just said it. It is the division property of equality. Now, we did discuss in class how this could also be the multiplication property of equality, because really you could think of this as multiplying by 1/4 on both sides. So I will accept both for that. 14. Find the measure angles. Okay, when you're given these pictures and you have to figure out the different angles, first thing you want to do is make sure everything's on your graph. So when I look at this, I see this, and I right away want to put a 90 degrees in there. Then I see some vertical angles. Do you guys see them? Here's two lines that cross. That means this is 90. I see more. I see this green one and this one. These make an X. So these two. So I already have measure of angle 2 is 77 and measure of angle 3 is 90. I just need that guy right there. And because we have learned that any angles, that is a linear pair. But it doesn't matter how many angles I put on there. All of them added together are going to equal 180. So I can look in here and I can find one straight line and add those up. So I could use this one, and this one, this straight line. I could use this straight line. It doesn't really matter. I'm going to actually erase these markings so that you know which one I'm picking. So let's pick this one right here. So then I know that all the angles on this side of that make up that line add up to 180. So I've got 90 plus the measure of angle 1 plus 77 equal 180. So now I just have to solve. So 90 plus 77 is 167. Why I put an equal there. And then we're going to subtract the 167 from both sides. And we're left with 13 degrees. So there are my 3 answers. And make sure you answer all of them when they ask you. All right, now we're going on to this one. And this is one of those more clearly vertical angles, isn't it? Because they only give you 2 lines. And they make an X, of course. And we know that the ones across from each other on 2 lines that cross are vertical angles. And we know that vertical angles are equal by the vertical angle theorem. So I can take these two and set them equal to each other. This angle, 3x plus 7, is equal to this angle, 4x minus 18. Now, I'm looking up here already because I'm curious. Did they ask me to get the angle measure or just the x? And here it's just the x. But you got to look, because sometimes they'll say, what's the angle measure? Which isn't too much harder, but it does take one more step. So I look and I see my 2 x values. I, of course, want to move my smallest x value just to keep things positive. You don't have to, but it does keep things positive. Now I want to add 18. And I get x equals 25. So we're done with that problem, but if I had said what are the angle measures, we would just substitute the 25 in here, and we would get 3 times 25 plus 7, 75 plus 7, 82. And just for good measure, I'll make sure this one also comes out to 82, because it should. 100 minus 18 is 82. Oh, good. They were the same. All right, our last page. Not getting into full proofs yet. You're still just justifying and practicing, because remember I said proofs take time. They take time to really fully absorb and understand how they work. All right, so when we look at this proof, let's first analyze it. We are given 1 is congruent to 2. I'm going to mark that. And we're also given 1 is 130 degrees. And I wrote that. Notice it says drawing not drawn to scale. So their point is we're not using a protractor and trying to measure. Okay. All right, so this was all given. So far so good, right? Now, what are we trying to prove? Measure of angle 3 is 130. We're trying to get these two connected somehow. So when I look up here and I want to know how is the measure of angle 2 equal to 130, well, I look up here and I think, oh, well, 1 was equal to 2 and 1 was 130. So can I substitute? Instead of measure of angle 1, could I just substitute and put measure of angle 2? Yes, and that's what we did here. That's called substitution. And it is equality, because we are dealing in equal signs right here. All right, so now in C, measure of angle, so we're trying to get connected to 3, okay? So we got now 2 is 130, so we're here. We're making progress. Now we're saying 2 is congruent to 3. Or not congruent, the measures are equal. The measures are equal. And I'm hoping you recognize the 2 crossed lines, which tells you they are vertical angles. So vertical angle theorem is what tells you, and that's my abbreviation for it, that's what tells you that any pair of vertical angles are equal. They have equal measure. They're congruent angles, they're equal measure. All right, great. So now I've got this. Great. So now can I substitute this into here? Just like I did above and get the answer? Because I have 2 is equal to 3. So now instead of 2, I'm just going to substitute the 3 in place of it because they're equal. So again, it's substitution. Property of equality. All right, last one. What is the value of x? Which of course they figured it out, justify each step. So they also give you this and they give you the graph. So whenever you're given these graphs or angles with things on it like that, or an angle like we did actually in class where there were angles and it's like 2x plus, kind of like, oh no, that wasn't a good example. An angle, something like this, where you have 2 angles. Let's say this is 3x and this is 5x plus 2, or something like that. I am just making it up. But remember in class we talked about how when you have 2 angles together, you need to start with the statement that this angle plus this angle is equal to the big angle. And that would be angle addition postulate. Or is that a property? I get them mixed up. And I won't hold your nose to the grindstone on those either. But as far as postulate or property. But that's how they're starting here. they're saying AB plus BC is equal to AC, the whole length. So instead of an angle addition, where this angle plus this angle equals a big one, we're talking about what kind of a thing is this? This is not an angle, this is a segment. So with this segment plus this segment's length is equal to this segment's length. Because remember, two capital letters together are a distance. It's a distance of a segment. So we're doing segment addition property. So it's similar to the angle, but dealing with segments. So we lay that out there, that when we add these two together, we get this. Well, then in the next step, look what happens here. So instead of AB, the distance from A to B, I put in what the distance is, which is 2x. And instead of the distance from B to C, I put in what it is. It's 6x plus 8. And then instead of the distance for A to C, which I don't have here, but look up here, I have it. I substitute in 32. So each one of these involved substituting. And it will be of equality. So we have an equal sign. All right, so then we're looking at this next step and we're saying, how do I go from here to here? So right now we're really trying to focus on just justifying, how to justify these different things. And hopefully as time goes on, we get the big picture for it all in the next chapter, hopefully. So when I look at this, I see 2x plus 6x is 8x. So that is called doing what? That's correct. Combining like, whoops, how about I spell right first? Don't report me. All right, combining like terms. Next one. How do we go from this step to this step? Well, you can see, what did they do? They subtracted 8, so it's the subtraction property of equality. And lastly, they divided both sides by 8, so it's the division property equality, which again, I would accept multiplication, but prefer division, especially on that one. When it's a fraction, it's a little trickier, but. And that is that. Let me see if there's anything else that I wanted to review. I do want to review one thing. Let's see. Let's flip this over. What if I said I had something like that. And I said that, let's see, the measure of angle ABD plus the measure of angle DBC was equal to 180. What would you give me for a justification? How can I say that? Now keep in mind, I'm not saying ABD plus DBC is equal to the measure of ABC. Okay, if I would have said that, that would be the angle addition property. I didn't. I said it was actually equal to a number, 180. What do you guys think? Linear pair theorem. That tells you if I have a linear pair, which you have, then the addition of it is equal to 180, the sum of the measures. Okay? Let's see, what else might I want to go over? Let me see here, let me see. Okay, let's talk about law of detachment and law of syllogism. There it is, I found it. Okay. So we have the law of detachment. and the law of syllogism. Remember, this one is similar to like a transitive property, except that there's how many if-thens? Those are true, then you can conclude that. There's 3 if-then statements. Whereas a law of detachment gives you 1 if-then, and then it'll give you a statement, and then you make the conclusion. So let's talk about an example for that. Let's see. I'm so bad at making things up. Let's try law of detachment. If you ran around the block, then you will be tired. Mrs. Silva ran around the block. What's your conclusion? Mrs. Silva will be tired, right? So I gave you the if part. I'm abbreviating, but okay. There's my if and my then. If Mrs. Silva ran around the block, then tired. Then if someone, I didn't actually say Miss Silva, sorry. If someone ran around the block, then they are tired. And then in the statement I said, Mrs. Silva ran around block. You would make the conclusion, Mrs. Silva is tired. Now what if instead I had set up here, I gave you the same thing here, but then I said Mrs. Silva's tired. Can you assume Mrs. Silva ran around the block? No, she might have just been up all night making a video for her geometry class, right? All right, I'm just kidding. It's like the middle of the day. Let's do the next one. Let's see here. If you work hard at school, then you will be happy. If you are happy, then you will smile. And I say, DeFore worked hard at school. What do you say? DeFore smiled. Exactly. Because well, wait a minute. No, time out. I'm jumping ahead too quickly. Forget that example. If you work, we have to put it together first. And then I was going to apply this to it. So let's put it together. So if you work hard at school. So I took the beginning part here. And then this is the connector. You will be happy. You will be happy. That connects the two. So I just take the beginning and the end. If you work hard at school, then you will smile. So now I can actually, that is the law of syllogism right there. But then I can also apply law of detachment and say, as I said, DeFore worked hard at school. And then you can say, DeFore smiled. So there we go. And I think I hit everything that I wanted to on there. It really does help if you find the the verbs in the sentences to try to break things down. Let me see what else. I think that's all. So take care, and I hope that helped. Take care. Bye.